Okay, well, I had fun with you guys this quarter. I don't know. I hope you had fun in this class. I think I'll talk about the final exam, let you guys know about that, and then you guys can ask me questions, and then we can cover whatever, right? Okay. All right. So we'll talk about the final exam for Stats 102A. All right. So first of all, the final will look nothing like the midterm exam. So, you know, you did well or you did bad on the midterm. There's like no overlap, okay? I mean, only that there is some R code on the final. Other than that, there's like, okay, so I'll just write, looks nothing like the midterm. So that may or may not be a good thing for you. I don't, everything in life is cumulative. No. It looks like nothing like the midterm. Okay, it's what it will cover basically numeric methods and Bootstrap and randomization tests, right? Which is everything we've done after the midterm. I think this makes sense, right?
Oh, yeah.
All right, numeric methods, Bootstrap. Hang on. Bootstrap and randomization tests. All right, so let me just talk about the numeric methods. So you need to be, I will not tell you which algorithm will be up here, but you know, be familiar with the root finding and optimization algorithms covered in class. Right. Okay, so that includes, I forget, what do we have? We have fixed point. We have Newton-Rapson. We have bisection and secant method, right? And then this is for root finding. And then for optimization, we covered Newton-Rapson, but really it could be also any root finding method applied to what? The derivative, right? Okay, so we have Newton-Rapson, we have golden section, and coordinate descent. Okay, so you need to be familiar with all of these. And the way, yes, question?
Sorry, does any of this include the binary stuff that we learned at the beginning?
Yeah, no, don't worry about floating point notation, okay? I mean, I'm not going to ask you to convert from binary to decimal or something like that, okay? All right, wait. What about what? No. ggplot, no, okay? But you got to be familiar with this, all right? And the way it's going to be, you're going to be tested on this, you'll need to bring a calculator and a ruler, okay? What is this groaning? Maybe calculator and ruler, and what I'm going to give you is I'm going to give you a function with a starting point, and I'll say do 2 iterations of one of these algorithms manually, right? So if I give you something like, so last year, someone, like, I'm assuming we can at least take derivatives of basic calculus functions, right? So like, so if you need to brush up on taking, your derivatives, brush up on that. It's not going to be like crazy. Just, I'm not going to have like super crazy functions, but like, what's the derivative of sine? Cosine, yes, okay. So yeah, okay. So yeah, basically, to test, I write a function with a kind of a starting point, or starting points if it's a secant method, right? Secant method requires 2 starting points. Okay, so I'll write a function with a starting point, and then I'll ask you to carry out maybe 2 iterations of one of the specified algorithms. Okay. To carry out, maybe 2 iterations of algorithm and graph them. Okay, so this is very easy. Like, you want to go home and practice, you just write up a function, right? Like 2x squared minus 3x minus 5 or something, I don't know. Okay, I don't know, I'm just making this up, and then just say like, okay, we'll start at x equals 2, and see if you can carry out some iteration and see like, where does this lead me, right? Huh? I'll probably graph the original function, and then you have to figure out the thing. Yeah, the ruler is so you can draw straight lines. Yeah. Huh? It's hard to draw straight lines without a ruler. Okay. Yes.
Do we need to draw the original function down, or
no? I will like, so I will write a function and I will graph the base function. Okay. Okay, I'll graph the function. Maybe I'll be nice and I'll graph the derivative. I don't know, depending on what the thing is. Okay, and then you've got to do what you're supposed to do, right? And okay. And then we'll and just for simplicity, for like golden section search, we'll say phi is 0.62, just so your math doesn't get like crazy complicated, right? We'll just, huh? This is the golden ratio. Huh? I'll write it down, okay? I'll write it down on the thing, like, if I were to give you golden section search, I'll say, for simplicity, use phi equal to 0.62 for the golden ratio. Okay, and that way you can find your locations easily. Okay, does that make sense for this? So be familiar with all of those algorithms that we've covered. I'll probably just pick like 2 of them for you guys to do. 2, maybe 3, I don't know, we'll see. Okay, and then okay, we'll have Bootstrap. In here you will have to, I'll give a problem and you will write code, okay? So this is probably going to be a Bootstrap hypothesis test. Oh, I'm telling you too much. All right. Okay, I give a problem and you write our code by hand. And you should be familiar with doing the Bootstrap yourself, doing Bootstrap using sample or using boot, right? So if you did it kind of coding it up yourself, you would sample with replace equal to true, or you could use boot. Okay. Bootstrap hypothesis test. I'll tell you too much. Okay, it'll be a non-parametric Bootstrap one. Okay. So, so don't worry. Don't worry about parametric Bootstrap. So, yes, question.
Are we expected to know how to conduct a bootstrap analysis?
No, we'll just do a Bootstrap hypothesis test, okay? So I know in homework 6 you've got the Bootstrap meta study, but we won't do that. We'll just have our data and you'll do the Bootstrap hypothesis test. It's like 6 lines of code, okay? Not even that, maybe. If you can count the closing curly brace as a line. Yeah, I mean, depending on how much you write, it could be more than 6 lines of it, probably. Okay. All right, so that's Bootstrap, non-parametric Bootstrap hypothesis test. Yeah, we'll just have one. It's very easy and reasonable. And then we'll do a randomization test. Randomization hypothesis test. Again, you will write our code by hand. Again, solution is going to be 10 lines of code or less, right? These are not crazy ambitious things. So, but you have to know how to do this. So, all right. So you'll write write our code by hand, and in both this one and the other one, you'll need to figure out how to get your p-value, right? So. Okay. And then, and then after that, we'll just have a few short answer conceptual questions. I'm sorry? Yeah, one randomization test, one non-parametric Bootstrap hypothesis test, 2 or 3 numeric method algorithms by hand, and then a few short answer conceptual questions. Yes?
Do we get the full 3 hours?
Yeah, you'll have the full 3 hours. I don't think it'll take the full 3 hours, but I'll just sit here And if you're at the end of 3 hours, that's fine. It's just, so I forget what time. I have to check the time. It's 8 a.m., right? So it's like, do I get my lunch at 11 or or earlier than that? So. How many questions total? I don't know. It'll probably be like 5 or 6 pages, but it'll be like, 1 page for each of these things. So it's reasonable.
Is short answer like a sentence?
Short answer is like 1 or 2 sentences. Like an example question would be, what's a good question that I can give you an example of without giving away the final? Okay. All right. We'll say only one root finding method is guaranteed to work, and under certain conditions. All right. What's the method, and what are the conditions? Okay. Do you know? What's the answer? Bisection method's the only one guaranteed to work. And what are the conditions to guarantee that the bisection method will work? It's continuous on the interval. And at one end is negative and the other end is positive, right? And the signs of the function are opposite on the interval. Okay, so if one side's positive and one side's negative, and if it's continuous, bisection method's guaranteed to find you a root. That's the only one that's guaranteed to work. All the other ones, we just hope work. Most of the time, a lot of the time they do, a lot of the time they don't. But it's like, okay. All right, so you'll have questions, not this question, but something like that, a little bit of a conceptual question covering these methods here. Okay. Any other questions? What's that?
Are the conceptual questions only covering the
Yeah, I don't know what kind of conceptual questions I can ask about. Yeah, okay, so the conceptual questions will cover, numeric methods and Bootstrap and randomization tests, yeah. Okay. So like when do you use a randomization test? When do you use a Bootstrap test? What are the appropriate, well anyway, okay. I don't need to give you all the answers. But, okay, questions about the final? All right, is that good? All right. Yes?
As for a calculator, is scientific calculator?
Yeah.
We don't need a calculator.
Yeah. Just any calculator is fine. Just not your cell phone, okay? So, or your iPad, or your computer, okay? You can't just say I'm using the calculator program on my computer. Sorry, that's not allowed. You want to use your calculator as a straight edge? Oh, I guess. It's okay. A ruler is a useful thing to have, and generally $1 or less, I think.
Okay, but I'm not gonna.
Okay. Yeah. But you know, like,
Oh yeah, that's smart.
don't.
Credit card.
What?
We're gonna use our credit card.
I recommend a ruler, okay? I saw somebody bring in like a piece of paper that they folded over like 7 times, and I was like, this is not a good straight edge, okay? That's perfect, okay? A 6-inch ruler, that's long enough, okay? You don't need. What's that? Yeah, you do not need to do a parametric bootstrap hypothesis test, okay? You might need to know parametric bootstrap hypothesis test for a conceptual question, okay? Maybe. Yes.
The finals in here.
Yes. It's in this classroom, okay? It's in this classroom at the time. I think 8 a.m. Is this one Thursday or the other one? Yeah, this one's Thursday at 8 a.m. I think the other one's like Tuesday at 8 a.m. or something. Okay, I'll be here. Okay. Well, I got 20 minutes left. What do you want to? You want to go over some concepts? No, I can't tell you the conceptual questions. Okay. All right. What do you have questions about?
Can you talk about how you get the algorithm for
The what algorithms?
for Newton Rapson? Can you talk about how you get it?
How do you get the Newton Rapson?
Algorithm.
Okay. All right. We'll review Newton Rapson. Okay. The idea is you have some function, and so this will be for root finding, right? So this is the root right here. This is what we want. And we will start here at x0. And here is f of x0. Okay. So what do we do for Newton-Raphson? All we do is we just draw a tangent line to the function. And this takes us to x1. So x1 is equal to x0 minus, and we want to figure out this length here, right? We want to figure out I don't know what just happened here. Okay. So this is my quote run, and this is the what we often say is the rise. Yeah. Okay. So we have run. Well, we have rise over run equal to f prime of x0, and what we want is the run. So we have rise divided by f prime of x0 equal to the run. So all we do is we just plug that in. And so the rise is f of x0 divided by the slope f prime of x0. So this is going to be what we do. And then at the next iteration, you just do the same thing. You go up, you draw a tangent line, and this will be x2. Okay, is that okay enough? Here, we can do, so let's say our function f of x is equal to x squared minus 5. And we'll say x0 is equal to 8. All right. So x0 is 8. And all right, so f prime of x would be what? 2x. Okay. So that's easy. So we start off, and we're going to say x0 is 8. So x1 will be 8 minus f of 8 divided by f prime of 8. Okay, so this is 8. F of 8 is going to be x squared 64 minus 5, so 59, divided by 16. I don't know what this is. This is why you need a calculator, okay? This is a little bit less than 4. 4 is 64, we're 5 less than that. 5/16 is 0.3125, so 8 minus 3.6875. 5, what's that? 4.3125, is that right? Okay. All right, and then, so that's x1, and then x2, we just do the same thing. All right, I don't feel like doing that, because I don't know what this squared is, but it's not going to be fun. Okay. I'll probably just tell you round off to 2 decimal places to keep our lives easy. So, okay, so this is easy, right? See this? You're going to make it a little bit harder than that. Okay. All right, is that okay for Newton-Raphson for root finding? All right, and then, I don't know, what else? What do you need for Newton-Raphson to work? You need to have at least the first derivative, right? Defined on the. It needs to be differentiable, yeah. Okay, and if you're going to do it for optimization, it needs to be twice differentiable. So, okay. Was there a question?
I just want to ask you about our final cover optimization.
Yes, I think I wrote that. It will cover optimization. What is optimization? What's a loose definition of optimization? Yeah, just finding the min or maximum of a function. Okay, whether that function be of 1 or 100 variables. Okay. No? Okay. Is this it? I was going to I don't know if you guys have any interest in learning about kernel density estimation just as a fun topic. No, you guys are all you guys are breaking my heart here, right? You don't care about this? You don't even know what it means? It's basically when you this is not covered. This was just a fun topic. A fun topic, right? Isn't all right, fun topics. Or I don't know. Destiny and estimation. This is from the best movie of all time, right? Okay. Kernel destiny estimation. All right. Yeah, that's not correct though. All right, so you do x here, and then you just ask density of x, and it produces this. But then you say, so if we ask the histogram of x, we get this picture. And if I say plot the density by midterm 10th week. Heard better lies. Maybe that's the truth. I have a midterm to take right now. I don't know. During 10th, Friday of 10th week midterm, right? Thanks. Yeah, okay. Maybe he meant to say final, to study for. Okay, so basically it's just, you have like, how do you go from, so we have a histogram, and we might say, breaks equals 20 or something, okay? And you might get a little bit more, a few more breaks or something into your diagram, but then can you draw a nice little smooth curve, right? Because we like seeing nice little smooth curves to represent the density of a function. We probably know how to make a histogram. How do we make this smooth curve? Yes? Yeah, what is bandwidth? Yeah, that's a good question. So I'll talk about all of this. Okay. Yeah, bandwidth. So kernel density estimation is all about just how do we make a nice little smooth graph. Okay. The basic idea. All right. Let's first talk about a histogram, because I think this makes the most sense. Is you got your data. Let's say your x is 2 data points, 1 and 2, right? And if I ask you to make a histogram, it would look like this, right? Or depending on how wide, so this would be like from 0 to 5 or something, it could look something like this. You could also, these would all be legitimate representations of the data. You could also have, if this is like 1 and 1.2 and 2 and 2.2 or something like that. So these are all legitimate representations of the data as a histogram. Kernel density estimation does something similar, okay? Except here we're just basically stacking bricks. We're just taking bricks and we're putting it on the number line. What you can think of for a histogram, yeah, you're stacking bricks. Just think of these as like bricks. With kernel density estimation, we're going to stack like soft mesh wires or something like that, okay? We're going to stack, quote, soft wires. All right. Mesh wires, I don't know if maybe not a mesh, okay? And our wires could be rectangular shape, okay? The wires can have different shapes, okay? And so we could, I basically have a data point at 1 and a data point at 2. I could take a rectangular wire and drop it right here. And then I would take another rectangular wire and drop it centered at 2, okay? So just imagine this here. And then when we represent it together, when these two drop and stack on top of each other, we're going to get a shape that looks like that. I don't know if you guys can imagine this wire thing or this soft shape falling down and another soft shape falling down on top of it, and we get a shape like this, okay? And I'll show you this. So here I'll call x will be 1 and 2, okay? And then I forget, what is the command? In density, we need kernel equal to rectangular. That's what we want. Okay, so we're going to do plot density of x with kernel equal to rectangular, right? And and this is what the thing looks like. We can alter something. This is with bandwidth. Let me go back to the help. Oh, it's called BW. All right, BW. Let me change this to 0.5. And so the bandwidth is how wide do we want these meshes to be, right? So I could do skinny mesh wires, right? So I could do just a little one and a little one, and this is what we'll get, okay? Or I could have like really wide ones. Here's one and here's two, and I could have like a really wide one and something that falls like this, and so we're gonna get something that looks like this. Okay, can you guys imagine these wires just falling on top of each other? So we have this, you know, so here if I, you know, do something like one, we get something that looks like that. If we have a little bandwidth, we'll get this. Okay, this is all that we're doing. And so if I do something like, if my data is 1, 2, and 2.2, when I plot this thing, you know, it's basically just stacking these funny shaped rectangles on top of each other, okay? And so this is what we have, right? So here is, you know, 1, 2, and 2.2. We get this, and depending on how wide I make my kernels, we get these odd-looking wire stacks on top of each other. Okay, so that's the basic idea. We're just taking little wire things and we're just dropping them centered at each data point. So in our case, you know, we had, you know, 1, 2, and 2.2. We're just dropping some of these wires on top of each other, and obviously this would be like a real pain to do by hand. If we had to like figure out how, like we say this is how wide my wire is going to be, and I'm going to have a bunch of these, and now I need to figure out exactly where it's overlapping and how tall it's going to be. It's a pain to do by hand, but with the computer it's not too bad, and we're just giving these instructions, and we don't have to do the rectangular one. Rectangular one is, I think, good for illustrating it, but we have other kernels, and the most common one is the Gaussian. And basically your wires that you're stacking, if you have 1 and 2, are basically Gaussian kernels, or these normal curves, and so when you stack them you get something that looks like this, or most likely the curves are probably at 1 and at 2 you get another one, and so they're probably going to look something like this when you stack them. And so that's going to be the kind of the default one. Let me just go back and say x is just 1 and 2. And the bandwidth is how wide you want your little mesh to be, right? So here at 1 and 2, I've got little these wires right there, and as the bandwidth, as the width of those wires grow, we can see the thing get wider and wider until, and this is kind of what we get here at a certain point, right? And I think, and the default, there's a formula for figuring out kind of the default bandwidth, and this is what it does, right? And you can imagine, you know, just putting one back at 2.2, going through this So here is, here I'll do 0.05, and you can see as we increase to 0.1, to 0.2, the thing grows and grows and grows, right? So we're just dropping these little wires on top of each other to get kind of the overall shape, and so that when we have a whole bunch of data points like this, we have R norm 100, and I'm going to do plot density of X, I get this shape, and I think, can I do a rug of X? And this tells you, like, these are all the actual locations of the centers of those things, right? I do this. Okay, and I don't know, you can see 1, 2, and 2.2. These are kind of the center of these things. And we have, there's several different curves. We've got the Gaussian, okay? You have rectangular. You have Epinechnikov. Epinechnikov. Yeah, it's basically an upside down parabola, right? So rather than just saying upside down parabola, the guy who used it said, I want my name Epinechnikov, all right? It looks funny because it's an upside down parabola. Let me just show you what that looks like. So plot density of X kernel Epinechnikov. Yeah, life is hard, right? Did I spell it wrong? Okay. Okay, so there's our two upside down parabolas. As they get wider, what does the middle look like? You get this funny nubbin here. Okay. So this is what your thing looks like. Generally, you wouldn't draw density plots when you only have 2 data points, but there's no rule against it. So let me just show you what it would look like on a regular. Here's 100 things. It looks a lot more reasonable there. Okay. Well, anyway, just a little. Very, very quick high-level overview of kernel density estimation, just so that that was fun? Okay, so yeah, because oftentimes you see density plots produced on your data, and I think it's a reasonable question, like, how did we come up with this density plot from the data? This is basically what we're doing. We're just adding these soft curves that on top of each other, rather than the histogram where you're adding bricks that are very rigid. Okay? All right. Thank you. Yeah, good luck, and please fill out your course evaluations if you haven't done so already. I appreciate that.
So I wasn't to the I forgot. It was the email from CAE.
Okay.
The one that he sent you.
I think so. Yeah, I gotta send him. the exams and stuff over, but I'll do that. Yeah.
I'll really do that.
Okay. No problem. Yeah.
Randomization part of it when we do
What's that?
we do use the randomization for the bootstrap.
Yes. There's you sample randomly with replacement.
So we use randomization as that when we sample the population or have to draw multiple samples from the
For the meta study?
No,
Or wait.
Just
Wait.
for the bootstrap.
For Bootstrap, so for Bootstrap you don't have the population. In regular Bootstrap you don't have the population.
Like I have.
But we draw like multiple samples from that.
Yeah, you resample your sample with replacement. Yeah.
So that's just like the randomization.
Yes.
Okay.
Yeah. But it is different. Randomization you shuffle your observations. With Bootstrap you resample with replacement. So it's a little bit different.
What's the difference?
So randomization. So if you have a deck of cards, randomization is you shuffle the cards and you deal out all 52.
Yeah.
Okay? With Bootstrap, you have your deck of 52 cards, you look at one, you put it back, shuffle it, you pull out another one, you put it back, and you keep going, you look and you sample with the replacement. And so with randomization, each observation appears just once. With Bootstrap, you might have one observation appear multiple times and some observations not appear again.
So randomization is replace equals to
True.
and then Bootstrap false. And replace
What-
equals
Replace equals true for Bootstrap. For randomization, yeah, replace equals false. Okay?
Daniel's next.
Okay.
Yeah. I decided.
I think you're here before me.
Fine. Are you having office hours next week?
I wasn't planning on it.
Why not?
Because I don't feel like driving into campus on Monday but I'll chime in on Piazza if people have questions and stuff. So. Okay.
I was here to this lecture.
Yeah.
I'm over there. So I have work I have to get to.
Okay.
And I was just wondering if I was going to miss anything different.
No, I mean unless they have different questions
Okay.
about
I'll just
stuff. Yeah, I don't think there's anything to be different. I'll cover what's on the final, and then if there's time left over, I'll do kernel density estimation.
Great.
So,
Thanks, Miles.
all right.
Alright, quick question. Do you mind looking at my code?
Sure, I can look, but I don't. Code is not a quick thing generally.
It's just the new team Rapson that I did just now.
Yeah.
I tried to code it out. But I'm just not sure why it's giving me such different values if I change x0. I think this is just from lecture, but I'm not sure if it looks okay.
So what happens when you do?
So when I do 3, it's like pretty close to it.
Okay.
The answer, the root is like
Yeah.
that, yeah. But then when I do like something like 8 or something. It's weird.
Oh, it's how many iterations are you doing? Let's see. Newton. I don't know. We try 7.
Yeah.
Okay, I don't know why. Is it just one? Maybe it's only doing one iteration.
Yeah.
Oh, wait, increment your, yeah, add a few zeros here, let's see. And then, that's strange, okay. X0, f of x0. Okay, just type in f1 of x0 or of 7. Let's just see, or 8. Yeah. Okay, that's correct. And then wait, at 8. Because this looks like the value after just one iteration,
Yeah,
so I feel like maybe something in our loop is not quite correct.
Because I think from the pseudocode you wrote in lecture, this was like exactly it. So I'm not sure.
Let me just.
Yeah, no worries.
I think. So x0 is 7, x new is this. Oh. I think we just, whoops. I think this will do the difference. I think this just needs to go there. Okay, this will work. Yeah.
Oh, perfect.
Yeah, I think your code was just, you had these 2 lines reversed so that it stops after just one iteration. Yeah.
Okay, got it. Thank you so much.
Oh,